I will also start recording. Okay. So
What is yours?
Yeah, you can start, Guillermo.
Okay. So hello everybody. I'm very happy to be giving this seminar online at the Instituto de Ciencias del Cosmos de Barcelona. So I will be talking about the cosmological anomalies and how they could be shedding light on the dark sector. And this seminar is based on some works that I've done during my first 2 years of PhD in the University of Montpellier under the supervision of Vivian Poulan. Well, needless to say, you can stop me at any point to ask for questions. Okay, so this is the general structure of my talk. I will start with a general introduction to concordance and discordance in cosmology. And then I will move to talk about the Hubble tension and how a model of early dark energy can resolve it. Then I will move to talk about a different anomaly, the so-called S8 anomaly, and how it could be giving hints about a specific scenario of decaying dark matter. And in the end, I will conclude. Okay, so let me start with the first part. So the last years of observations have led to establish a concordance model in cosmology, which is called ΛCDM, whose main ingredients are big amounts of dark energy and dark matter, and also some tiny amounts of baryons, photons, and neutrinos. And this model also has two important assumptions. One of them is that the universe is isotropic and homogeneous on very large scale. This is the cosmological principle. And it also assumes that gravity is correctly described by general relativity. So in its minimal form, this model is fully specified by only 6 parameters, which are controlling essentially the energy content of the universe, some details about inflation, and also a parameter controlling star formation. So with only these 6 parameters, this ΛCDM model is able to provide an excellent fit to the anisotropies of the cosmic microwave background that I'm showing here, and which corresponds to the relic radiation that was formed shortly after the Big Bang. But in addition to that, it also explains very well the observation that we have of baryon acoustic oscillations, the luminosity distance to supernova 1A, the abundance of light elements such as helium or hydrogen, and also the distribution of large scale structure in the universe. So this model has been extremely successful. However, it faces several challenges, and maybe the most important is the fact that it doesn't provide an explanation for the nature of its main constituents, dark matter and dark energy, which is what we typically call the dark sector. In particular, this model doesn't tell us whether these components are made of particles or not. It doesn't tell us whether they are made of a single species or several species. It doesn't tell us about anything about the production mechanism or any other properties, such as the lifetime or the mass. And another challenge has appeared in the recent years with the increase in precision in cosmological data, and it is the appearance of several experimental discrepancies in the determination of some parameters. So for example, we have a mild discrepancy in the determination of the S8 parameter, which is essentially measuring the growth structure. And we have also some disagreement in the determination of the current expansion rate of the universe, the Hubble constant. So in general, there are 2 possible explanations for these anomalies. One of them is that we might have been missing some systematical error in some of the experiments. And well, this is definitely the less exotic explanation. However, as we will see, there are many different experiments that see this tension. So it is very difficult that a single systematic error will be able to account for all of them. And then another possibility is that we might have been assuming the wrong model all the time, and we are not correctly interpreting the data. So that if we assume a model beyond ΛCDM, we might put these measurements into agreement. So for me, the very nice thing about that is that this could reveal some properties about the very mysterious dark sector that I was mentioning before. But the problem is that it is very challenging to build a model that fits all the data as well as ΛCDM. Okay, so let me start talking about the SA tension. So which comes when we talk about the weak lensing surveys. So these surveys essentially measure the distorted images of galaxies due to the presence of large clumps of matter in the line of sight. And in this way, they are able to get an estimate of how matter is distributed in the universe. This distribution of matter is well captured by this parameter combination that we call S8, and which is given by this expression, where omega m is the abundance of matter in the universe, and sigma 8 is giving us the amplitude of matter fluctuations on a scale of 8 megaparsec. So this sigma 8 parameter is essentially telling us how clustered are the galaxies in the universe. So it turns out that the direct determination of this parameter by the different weak lensing surveys gives a value that is between, I mean, it depends on which weak lensing survey you look at, but generally it gives a value that is between 2 to 3 sigma smaller than the one you indirectly obtain with Planck, assuming the ΛCDM model. So, well, this is all I have to say for the moment about the SA tension, and I will come back to it at the end of the talk. So now let me move to discuss the Hubble tension. So this refers to the 4 sigma tension between the indirect determination of the Hubble constant by the Planck satellite, again, assuming ΛCDM, and the direct determination by the SUS collaboration, which uses a cosmic distance ladder method. In particular, it calibrates the distance to supernova using CF8 variables. So here I'm indicating the values of these 2 measurements, but these are not the only measurements that measure the Hubble constant. There are many more, and here I'm just making a selection of some of them. And what one realizes by looking at this is that when one considers probes of the universe that use some high redshift information, one typically gets a small value of the Hubble constant. This is the case, for example, when you combine observations of BAO, baryon acoustic oscillations, with big bang nucleosynthesis, but also when you consider other CMB experiments different from Planck, such as ACT. On the other hand, when you look at observations that measure the Hubble constant more directly using some low redshift information, you typically get values that are higher, such as, for example, the SUS measurement that I was mentioning before that calibrates the supernova with Cepheids, or also other observations that use the gravitational lensing of quasars. It is fair to say that there are some measurements, such as the one carried by the Carnegie Chicago Hubble program, that calibrates supernova not using Cepheids, but using the tip of the red giant branch, which gives a value that is right in the middle of the one obtained by Planck and the one obtained by SUS. And then we are also starting to have measurements of the Hubble constant using gravitational waves. This is what I'm showing here in green. But right now the error bars are so big that it is that we cannot conclude anything. But in the future, when these measurements improve, this will be decisive in settling the debate. Okay, so now I would like to explain a bit more how the SUS collaboration determined and in general, the cosmic distance ladder method determined the Hubble constant. So they essentially use a relation that was proposed by Hubble almost a century ago. So they measure the recession velocity to some object, and this is something they can obtain simply from the redshift information. And they also measure the distance to that object. And in general, you will want this object to be a standard candle, such as supernova 1A. This means that it is an object for which you can calibrate the intrinsic luminosity using some technique. And then by comparing with the observed flux, you can obtain the distance to that object. So once you get this measurement of the velocity and the distance, you can get the Hubble constant from this relation. In practice, things are a bit more complicated because the Hubble rate is evolving and depends on the energy content of the universe as given by the Friedmann equation. And the distances itself depend on the Hubble rate. So in order to avoid this problem, people typically focus at nearby objects and therefore a small redshift. So one can carry out expansion at a small redshift in this luminosity distance and recover the expression that I was showing before. So this is the reason why people typically say these kind of determinations are very model independent. Okay. On the contrary, the way the CMB determines the Hubble constant is very model dependent. In particular, what the CMB, or the Planck collaboration, determines with a very high degree of precision is the angular size of the sun horizon. Okay, and what is this? So essentially in the early universe, we had a soup of electrons, protons, and photons interacting very strongly, and which had a very strong pressure. This pressure counteracted the effects of gravity and led to the formation of sound waves. So this sound horizon is essentially the distance traveled by these sound waves up to the moment of recombination. And it depends on the energy content of the universe at this time. So this is the quantity that appears in the numerator of this angle. And in the denominator, we have the angular diameter distance to recombination, and depends on all the energy content of the universe after recombination at late times. So this angular diameter distance is actually the only quantity that is directly related to the Hubble constant. And from here, we can already see how the CMB determines the Hubble constant. Essentially, a given model, such as ΛCDM, will give us a prediction of the sound horizon. And then combining this with our measurement of this angle, we will be able to obtain the Hubble constant. So this already suggests two different ways of approaching, of trying to solve the Hubble tension. So one way is to try to modify the universe at early time. And what one would like to do is to reduce the sound horizon. And since this angle, theta, needs to be fixed because it's very well measured, we also need to decrease the angular diameter distance. And this will lead to an increase in the Hubble constant. So a prototypical example of this is just to consider some extra relativistic degrees of freedom in the very early universe. But it has been already shown that this simple solution doesn't work. Okay, so these are the early time solutions, but then one can alternatively consider modifications to the late universe, to modify the universe after recombination. So for this type of solutions, the sound horizon is fixed by construction, and therefore the angular diameter distance is fixed as well. But what one changes is the integrand of this angular diameter distance, and it is changed in such a way to allow for a higher value of the Hubble constant. So in this case, a prototypical example of model that achieves that is just to consider dark energy with a phantom equation of state. But in a similar way to the delta N effective model, it has been shown that this simple approach doesn't work. Okay, are there any questions for the moment? Or... Okay, I will move on then. Okay, what is needed to resolve the Hubble tension? So this is a question that has been addressed in several model independent ways. And the two main conclusions that have been extracted are the following. First, the late time solutions appear to be almost excluded once one considers a combination of BAO and supernova data. And for early time solutions, one seems to require a decrease of the order of 7% in the sound horizon. So this is very nicely summarized in this plot from a famous paper by Knox and Millet. And what this plot is showing is the direct determination of the Hubble constant by the SUS collaboration in orange. And then it is also showing us the determination of the Hubble constant and the sound horizon by Planck, which, as I said before, is very model dependent. And finally, in green, it is showing us a determination of the Hubble constant and the sound horizon obtained using BAO and supernova, and which is very model independent. Okay, so let me tell you how this green band is obtained. It uses what is typically called an inverse distance ladder method. So this is what I'm describing here at the right. Essentially, for a given value of the sound horizon, you can get the corresponding value of the angular diameter distance using the BAO data, because these measurements constrain, among other things, the ratio between these two quantities. And then once you have the angular diameter distance, you automatically can obtain the luminosity distance to supernova because there is a very simple relation between the two of them. And once you have this angular diameter distance, no, sorry, this luminosity distance, comparing with the observations of the apparent magnitude of supernova, that I'm calling here M, then you can obtain the Hubble constant from the calibration constant. So this is the method that is giving us this green line, this green band, sorry. And yeah, this already summarizes the 2 points that I was saying before. Late time solutions cannot work simply because by construction, they cannot reduce the sound horizon. And for early time solutions, you need to decrease the value of the sound horizon because the combination of B and supernova is forcing us to move in this direction. Okay, so yes, this was the first part of the talk. Now I will move to talk about a particular scenario of early time, a particular scenario of early universe, which is called early dark energy, that achieves precisely this reduction in the sound horizon and can resolve the Hubble tension. So I don't know if there is any question for the moment. I hope I'm not going too fast.
No, I think you're doing well.
Okay.
So, well, so far for those who are very related, I mean, we are like very working in cosmology. This is well known, but that's good because there are other people in the room who are not familiar with this kind of data. So that has been so far a very nice introduction.
Okay, good. Yeah, now maybe it will become a bit more technical for those that doesn't do cosmology. So yeah, don't hesitate to interrupt me at any point. Okay. Yeah, so what is this model of early dark energy? Essentially, it is just a scalar field whose dynamics are dictated by this modified action potential. And what this potential achieves is the following. So initially, the scalar field is frozen at this part of the potential. And later, when the Hubble rate decreases below the effective mass, then this scalar field starts oscillating about its minimum and it starts diluting in a way which is faster than radiation. So in order to illustrate that, here I'm showing the redshift evolution of the energy densities of different components in the universe. And in particular, in purple, I'm showing the evolution of the energy density in the early dark energy component. So, well, since this is redshift, here it is the past, and here at the left is the present. So we see the early dark energy initially undergoes a phase where it is frozen. So it behaves as a cosmological constant, and this is actually the reason why we call this kind of models early dark energy. And then at a certain redshift, it starts to dilute in a way which is faster than radiation. So the interesting thing about that is that these features lead to a very peaked shape of the energy injection that I'm showing here. And this injection of energy at early times boost the Hubble rate at early times before recombination, and therefore can reduce the sound horizon, which, as I was explaining before, is a key ingredient in order to solve the Hubble tension. So in general, this is a 3-parameter model. And the extra 3 parameters that this model adds with respect to ΛCDM are the fraction of early dark energy at the redshift in which it becomes dynamical. Then the second parameter is the redshift at which it becomes dynamical. And the last one is the initial value of the field, the initial value of the scalar field. Okay, so what my advisor and his collaborator were showing a couple of years ago is that this model of early dark energy can resolve the tension, the Hubble tension, if this early dark energy constitutes around 10% of the total energy of the universe around the time of matter radiation equality. So this is something that can be seen here in the results of an analysis that includes Planck, BAO, supernova, as well as information from SUS. Okay, so this is very nice. This model appears to solve the tension, but it has some caveats. For example, it faces some fine-tuning problems. For example, it doesn't tell us why this scalar field starts oscillating precisely around the time of matter radiation equality. So in order to explain that, there has been already some proposals that try to connect the early dark energy with the neutrino sector. And there have been also some interesting proposals that try to connect this early dark energy component with the late time dark energy that is responsible for the present acceleration of the universe. And another caveat of this model, and which we can see here in this plot, is that in order to preserve the fit to the CMB, these kind of models predict a higher value of the cold dark matter density. And this leads inevitably to a higher value of S8. And this is something that has been shown to be very generic for any kind of early universe model. So the problem of increasing S8 is that in this way we are rising the tension with large-scale structured data that I was mentioning before. And so this observation has been used by several authors to show that when you add a large-scale structured data to the analysis, for example, weak lensing data that I was mentioning before, then you restrict the success of the resolution. And this author was showing in addition that if you consider only Planck data alone, you actually don't detect early dark energy. So all these facts led these authors to conclude that this model of early dark energy is actually ruled out as a resolution. Okay, is there any question until now, or? Okay, if not, I will go on. So we wanted to examine this claim that the early dark energy solution is ruled out. And what we actually found is that the early dark energy solution is very robust. So in order to justify this, we wanted to address mainly two questions. The first one is, why is early dark energy not detected when you only include data from Planck? So this is due to, we found this is due to a very strong chi-square degeneracy in Planck data between these two models. And what do I mean with that? What I mean is that once the value of the fraction of early dark energy is very small, but not zero, the impact of these other two parameters, the redshift at which it becomes dynamical and the initial field value, they essentially become irrelevant. And in terms of chi-square, we get the same predictions as lambda CDM. So what this makes is, this leads to posteriors that are more naturally weighted towards lambda CDM. And this is something that we can see here in this red curve, where we are showing the constraints on the fraction of dark energy using the 3-parameter model that I was mentioning before. And we see that the best fit value is very close to the 2 sigma exclusion limit. So in order to avoid this problem of Bayesian volume, we have considered a 1-parameter early dark energy model where we fix the values of these 2 parameters of the redshift ZC and the initial field value, and let the fraction of early dark energy free to vary. And in this way, from Planck data alone, within this 1-parameter model, we are able to detect the early dark energy at 2 sigma. So yeah, this provides a clear explanation of why we don't detect the early dark energy just from Planck data. And yeah, the second question we wanted to address is whether the large-scale structured data, such as the weak lensing surveys, constraining enough to rule out the resolution given by the early dark energy. So the first thing we want to check in order to do that is to compute the nonlinear matter power spectrum. So the problem is that in general, this is very computationally expensive. And what one typically uses is allofit. So allofit is just a set of fitting formulas that are obtained by fitting the results of n-body simulations. However, these n-body simulations assume lambda CDM. So it is not clear that you can use this allofit algorithm for models beyond lambda CDM, such as early dark energy. So what we did is to carry out several n-body simulations for the early dark energy cosmologies, and we found that they agree very well with the results of allofit. So this is, for example, shown here in the red curve. We are showing the nonlinear matter power spectrum. So here the triangles and the crosses are showing the results of the n-body simulations, and the solid lines, the solid red lines, are showing the results of the allofit algorithm. So we see that they actually agree very well. So now that we have the calculation of the matter power spectrum under control, we can go and test against the large-scale structure data. And in particular, we tested, well, we took our baseline combination of data, which is Planck, BO, supernova, and SUS. And then we also add the weak lensing data from KITS, Viking, and DES. And what we found at the end is that the S8 tension persists. It's true that this model is not able to solve it, but the fit is not significantly degraded with respect to ΛCDM, and the solution to the tension essentially survives. Okay, and regarding the prospects of this model, it has been shown that future CMB experiments, such as CMBS4, will be able to unambiguously detect early dark energy. So this can be seen here in this plot that is showing as the result of a forecast analysis on early dark energy that is using mock data from CMB stage 4. And another interesting thing is that other current CMB experiments, such as ACT, are already showing a detection at the level of almost 3 sigma of early dark energy. So this is something that was shown in this paper that appeared last month. And yeah, with all of this, what I just want to say is that the current situation of early dark energy is still not clear. And we need to wait for more data, for more precise data in order to see whether the resolution to the tension provided by this model really survives. Okay, so what remains clear is that this model is not able to address the S8 tension at all, and this is what we wanted to explore with another different model, and this corresponds to this other part of my talk. So, well, before starting with this part of my talk, I want to ask you whether there are any questions on the first part.
Yes, I have a question. Can you hear me?
Yeah, I hear you well.
Can you please go back to the why Planck cannot detect EDE?
Yeah, sorry, sure. Yes, here.
So just to clarify, first, the 1P and 3P, what are they exactly?
Yeah, the 3P is just considering 3 free parameters in the early dark energy. So it is essentially, sorry, let me go. Yeah, it is taking these 3 parameters as free. We let them vary and constrain them with the data. And the 1P and the 1P ED, we are fixing these 2 parameters to some fiducial values, and we let only the fraction of early dark energy as a free parameter.
Okay, but so in your model space, first you start with the degeneracy. So the 2 models are sort of overlapping, right?
Which 2 models?
ΛCDM and EDE. There's some degeneracy. So
yes,
then you say, okay, let me fix 2 parameters and that only one vary. But if you fix these 2 parameters by hand, no?
Yeah.
Then you sort of break the degeneracy by hand, but it's not broken on its own, you know? It's something like being forced, if I understand correctly.
You break it by hand. I mean, what I'm just making is to allow the Monte Carlo to explore the space parameter well, because if we don't fix these parameters, a big volume of the parameter space is spent on a region that it is essentially identical to ΛCDM in terms of chi-square. So yeah, indeed, we are kind of breaking this degeneracy. But what we find is that only from Planck data alone, we are able to. Sorry, I'm not sure if I understand your.
It's okay. We can talk about this at the end. Thank you.
So before you go on, Samuel has also raised his hand. I want to ask a question.
Yes. Hi, Guillermo.
Hello.
So I have one question about the sigma 8 tension. I think it was one slide before, slide 17.
Yes.
Yeah, exactly. About so here it looks like there's also a change in slope, and this change in slope makes goes into the sigma 8 tension. So can you remind us, like, on this plot, and what are the scales that are mostly probed by CMB, and what are the scales that are by Hubble tension? So I was thinking whether if you combine this with neutrino mass or something else, that you could solve the Hubble tension, the sigma tension by combining early dark energy with neutrino mass or something like that.
Yeah, this is a very good question. Thanks. So first of all, the CMB measured roughly after 0.1 inverse megaparsec. And the interval of values that are important for computing S8 are between 0.1 and 1 inverse megaparsec. I should have highlighted this, but yes, essentially this. So yeah, we see in this interval, precisely in this interval, the early dark energy leads to an enhancement in the power spectrum with respect to lambda CDM. And yeah, I would like just to mention that this is actually not due to early dark energy itself, because the intrinsic effect of early dark energy is actually to suppress power, but it's just due to the fact that we have shifted the value of some of the lambda CDM parameters. So this increase in power is essentially coming from the fact that early dark energy requires a higher value of the cold dark matter density in order to fit the CMB data well. And indeed, one could think that just adding massive neutrinos to the gain could solve this tension, but we already tried that in the past, and it doesn't work. You don't get a suppression that is high enough. But yes, it's a good point.
Okay, thank you. Because in this plot, it looks a bit like as if it was like similar to a scale-independent slope, but it's a scale-dependent change in slope, right?
Yeah, it's a scale-dependent. Yeah,
it's not like primordial NS. All right.
Yeah, no, it's a scale-dependent indeed. Yeah.
All right, thanks.
I typed a question. I don't know if you
want you can
I can say
yes.
That. So let me ask the question of a skeptical. So or a skeptic, what would be the smoking gun of, say, you say, yeah, early dark energy is really out there. It's what it is. It's what actually explains the H-naught tension. So what will be the feature that I should be looking for in the data? And does it even make sense to ask a question like that? Because one thing is, I do an MCMC, I constrain the parameter of the model, and it turns out that this model is a better fit than that one because I added one or two parameters. And then we can go into evidence and, model selection and things like that. But if I want to be really skeptical, I say, can you point your finger on a plot and show me, this is the baseline lambda CDM. You see this bump there? That's the EDE signature. That's their feature. That's their fingerprint. Is there a fingerprint?
No, this is a very good question. I mean, I haven't included a plot here, which I should, but essentially, if you look at the residuals in the CMB, it's true that with the current precision of the current experiments, you are not able to disentangle the early dark energy for lambda CDM, but for future experiments such as CMBS4, you will be able to really get, if early dark energy exists, future CMB experiments will be able to really detect them. Now, I don't know if this is a smoking gun because there is maybe some degeneracy with other models. And yeah, I would like to think about alternative probes apart from CMB that are able to probe univocal in a very unambiguous way early dark energy. But from the top of my head, I'm not sure. Because the effects of their model are, it's purely gravitational. So for me, it's hard to think other signatures that could lead apart from the CMB. So
it would have to be in the CMB, right? Because you are changing things before, basically before a combination, and after that, everything is unchanged. So it has to be in CMB. There's everything else is only seen as a mismatch of cosmological parameters. Yeah. And the problem is that in the CMB, everything is degenerate with everything else because we are trying to constrain zillions of parameters. And at the end of the day, we have effectively three curves, not completely independent, T, TE, and EE. That's all we have.
Yeah.
Okay, thank you.
No, thanks for your question. Okay, is there any other question?
No, I don't think so. You can keep with the talk.
Okay, very good. So yeah, this is another project where we were trying to relate the Z tension to decaying dark matter, and this is a project that I've done in collaboration with Ricardo Murgia, Vivian Poulan, and Julia Laval. Okay, so I was mentioning the state tension before, but now I would like to try to explain what is really needed to resolve this tension. So here I'm reminding the expression for the state parameter that is given by this combination of omega matter and sigma 8. And yes, there have been some recent analyses that have combined results of wing lensing from kits and results of galaxy clustering from BOSS and have led to what is shown here in red, to this red contour. And now I want you to have a look at this red contour and compare with this green contour that are showing us the determination of sigma 8 and omega matter from Planck. So what we see from this is that what is driving the tension is actually not omega matter, but sigma 8. So the first thing is that if you want to consider some exotic model that tries to address this tension, that tries to increase the value of S8 to make it in agreement with Planck, what one needs to do is not to change omega matter, but to change sigma 8, to suppress sigma 8. So, yeah, sorry. So this sigma 8 is given by an integral of the matter power spectrum with a certain window function, and this window function is selecting an interval of scales or between 0.1 and 1 inverse megaparsec. So in order to reduce the state parameter and make it in agreement with the weak lensing, you need to suppress power with some model at this interval of scales. So a priori, there are a lot of mechanisms that have been proposed to suppress power. And one of them is, for example, warm dark matter. This has been known for a long time, but the problem is that the warm dark matter is very constrained by many different probes. And it has already been shown that warm dark matter is not able to provide the amount of suppression you need at these scales. So for this reason, it is worth to explore other models that also produce other more exotic models that also produce power suppression. And this is why we wanted to study the dark matter decay. So in particular, we have studied a scenario where dark matter decays to two types of particles. It's a two-body decay. So it decays to massive and massless particles. So what we call dark radiation and warm dark matter. And well, these particles, the decay product, are assumed to not interact with the standard model. So that's why we say both of them are dark. And this kind of two-body decays adds two extra free parameters with respect to ΛCDM. One of them is the decay rate of the dark matter, gamma. And the other is epsilon, which is the fraction of energy that the dark matter transferred to the massless component. And it is given by this expression, by this ratio of masses. So what this epsilon parameter is also telling us is about the thermal nature of the decay product. So we can understand this by looking at the lower and upper limit of this epsilon parameter. So the lower limit of epsilon is 0, and this corresponds to the case where these two masses are equal. And this is actually ΛCDM, because what this says is that the massive daughter has the same, sorry, the massive daughter has the same mass of the dark matter, so it is diluting in exactly the same way. And then the upper limit corresponds to 1/2, which is when the masses of all the decay products are 0. And we are essentially recovering a case in which dark matter decays to only dark radiation. So we can see this epsilon parameter as effectively interpolating between these two regimes. But we will also see that intermediate values of epsilon are able to lead to some interesting effects on the matter power spectrum. So yeah, is this clear, this introduction to the two-body decay? Okay, so I will move on. Okay, and what's the current status of this kind of decays in the literature? So, well, this paper that came out in 2014 was really the first one that was using a full treatment of perturbations, but they didn't do any kind of parameter scan simply because the calculations were very slow. And then this model got renewed interest in 2019 because it was actually proposed as a resolution to the Hubble tension. But it was shown later that a combination of supernova and VEO and also CMB rule out the resolution. And this is actually kind of to be expected from the argument that I was saying before, because this is a late time modification to the universe. So you don't expect this kind of models to solve the Hubble tension. However, all these last papers have been lacking an accurate treatment of perturbations. And in order to assess the impact on this other tension, the S8 tension, it is essential to treat the perturbations accurately. So this was the goal that we had for this project. We wanted to perform a full parameter scan, including a complete treatment of linear perturbations in order to see the impact of this model on the S8 anomaly. So in order to accurately treat perturbation, we need to track the elements of the perturbed stress energy tensor for all the different species. So this corresponds to delta, the overdensity, theta, the energy flux, and sigma, the shear stress. And we need to track this for the three species involved in the decay: the dark matter, the dark radiation, and the warm dark matter. So the more generic way to do that is just to consider a Boltzmann hierarchy of equations, which dictate the evolution of the phase space distribution multiples. And for dark matter and dark radiation, the treatment turns out to be very easy because all the momentum degrees of freedom can be integrated out. But unfortunately, for warm dark matter, one cannot do this simplification, and one needs to follow the evolution of the full phase space distribution. And the problem is that this can be very computationally expensive. One might need to solve the order of 10 to the 8 ordinary differential equations, and making any kind of cosmological analysis completely impossible. So in order to solve this issue, I devised a new set of fluid equations to describe the perturbations of this warm dark matter, and which are based on a previous approximation for massive neutrinos. So these are the equations that I derived and which give the evolution for the overdensity and the energy flux of the warm dark matter. And they also involve two different sound speeds whose expression I'm giving here. So I don't want to enter into the details of these fluid equations, but the only thing I would like to remark is that the red terms that the terms that I'm highlighting here in red are the terms that appear due to the decay. So if we set all these red terms to 0, we are essentially recovering the fluid equations for massive neutrinos that have been proposed in the past. And the advantage of them is that they massively speed up the computation, reducing the CPU time from 1 day to only 1 minute, and therefore allowing us to now perform a full parameter scan. Okay, yeah, is there any question regarding all these last things I said? Okay, so yeah, I will we'll move on. So now that we know how to compute the perturbations of the species, we can have a look at the impact on the observables, and in particular at the impact on the matter power spectrum. And so the main effect actually arises due to the warm dark matter, and it is a suppression at the small scales, in particular at the scales smaller than the so-called free streaming scale. So in order to illustrate that, here I'm showing the residuals in the matter power spectrum with respect to lambda-CDM. So on the left, I'm fixing epsilon and barring gamma, and on the right, I'm doing the opposite. I'm fixing gamma and barring epsilon. And what we can see from here is that the effect of gamma is to control the depth of the power suppression, the amount of suppression, which is to be expected because this is telling us how much warm dark matter is produced. And then the epsilon parameter is controlling the cutoff scale, that is the free streaming scale. So what we see from here is that some intermediate value of gamma and some intermediate value of epsilon should be able to give us precisely the amount of suppression that we need in order to explain the low value of S8. So in order to test this idea, we have carried out a Monte Carlo analysis using a combination of Planck, BEO, supernova data, and a prior on S8 from this weak lensing analysis that combine data from KITS, BOS, and 2DF lens. And the results of this analysis are shown here. We are showing here the posterior distribution for the relevant parameters. And what we see is that the values of S8 that we reconstruct are actually in excellent agreement with the weak lensing data that we use, and which is indicated here by the green band. And also, in order to gauge the importance of this resolution, we are comparing also with another model that I call nu lambda CDM, which is essentially lambda CDM, but having the mass of the neutrinos as a free parameter. And what we see is that the decaying model performs much better in explaining a low value of S8 than the than the neutrino model. And in particular, it gets a much better fit in the value of S8. And yeah, this improvement in the fit, we get a delta chi-square of -5 with respect to this lambda CDM model with massive neutrinos. This negative delta chi-square drives a weak preference for a model in which dark matter decays with a lifetime of around 55 gigayears and transfers around a fraction of around 0.7% of its energy to the massless daughter. Okay, but now one could ask the question, why is it that this two-body decaying model performs better than this other model that also gives a power suppression, which is the massive neutrinos? And the key here is that it's because of the time dependence of the power suppression. So here on the left, I'm showing the residuals in the matter power spectrum with respect to lambda CDM for two different models. So in red, I'm showing the residuals for our best fit decaying model. And in blue, I'm showing the residuals for lambda CDM, but having a very high mass of neutrino masses. So having a 0.27 EV. This value is just chosen because it gives the same suppression as the decaying model. And we are also showing this for two different redshifts. And what we see is that the amount of suppression in the decaying model at high redshifts is actually very small. And this is simply due to the fact that in the past, there was less warm dark matter that was produced. On the contrary, the amount of suppression in the massive neutrino model is very important at all redshifts. And this leads to very strong effects on the CMB spectra that rule out the resolution. So this is what we are showing here at the right, where I'm showing the residuals in the temperature and lensing spectra for these two models, and here the gray bands are indicating the error bars. So we see that the neutrino model gives effects that are already too strong to be allowed by data. So yes, this is the main reason why this model performs better than, for example, massive neutrinos. But the interesting thing is that this model has also some implications beyond explaining the S8 anomaly. For example, from the model building point of view, it would be interesting to understand why data in general favors very small values of epsilon, which correspond to a very small mass splitting. And there was recently a paper in which the authors built a model in the context of supergravity, which precisely reproduced this kind of decays and also provided a natural explanation for this small value of epsilon, for this small mass splitting. This model could also have implications for the so-called small-scale crisis of lambda CDM, because in the past, people were carrying out n-body simulations for this kind of decaying models, and they saw that they lead to a reduction in the abundance of subhalos, as well as the concentrations. And finally, it could also have some implications for the recent xenon one-ton excess, because it was proposed in this paper that this excess can actually be explained by a fast dark matter component. That is, dark matter having velocities between 5 and 20% the speed of light. So this cannot be the cold dark matter that is assumed in lambda CDM, but it could be the warm dark matter that is produced in the decays, with this epsilon parameter essentially playing the role of the velocity. Okay, and regarding the prospects of this two-body dark matter decay, here I'm showing the redshift evolution for the growth factor, and I'm showing this for two models. One is a lambda CDM, and the other is our best fit decaying model. This is indicated with the dashed lines, and I'm showing this together with several experimental constraints. So what we see is that the current experiments are not able to disentangle between these two scenarios. But future surveys, such as Euclid or LSST, which will measure this quantity with very high precision, will be able to disentangle between these two scenarios. So the next natural thing to do is something that we are already working on, is to predict the nonlinear matter power spectrum for this kind of decaying model in order to be able to fit with the full shape spectrum that is measured by the weak lensing surveys and not only take a prior NSA. So to do really a more careful data analysis by taking into account the nonlinearities of this model. Okay, is there any question? Okay,
yes, I would have a question. So have you thought about how degenerate this model is of the decaying dark matter with respect to baryonic effects? So if you compare it to the suppression due to baryonic effects on the galaxy formation and AGN feedback, all of this, I think they would provide suppression on similar scales, no?
I see.
Roughly. Or would it be possible to degenerate this baryonic effects from the model? And what about these other probes that you mentioned, for example, the xenon experiment? Could this also be this excess also be explained by baryonic feedback, or there you really need a different type of dark matter to explain this?
Yeah, it's a very good question. We haven't done the exercise of explicitly checking the degeneracy with baryon feedback, but I only expect some degeneracy at late times, because what I find nice about this model is that it leads to a very particular time dependence of the power suppression. So at early times, at high redshift, the power suppression given by this model is very small. Well, I'm guessing for baryon, this power suppression is important for a wide range of redshifts. So if we use probes that also give us information at high redshift, I think this could break the degeneracy between baryons and the decaying dark matter. And regarding the xenon quantum, I'm not sure. I mean, there have been other proposals for explaining this excess, not only this fast dark matter component, but I don't know if in baryon, well, apart from the systematics that there could be in the experiments, I don't know if there has been some baryon feedback that has been proposed to explain this as well. Yeah, regarding this, I'm not sure. I'm sorry, but yeah.
Yes, thanks. Yes, so for the redshift dependence, I agree that this would be, for sure, there would be some different behavior between the models. What I am more concerned about is how to model exactly the redshift dependence of this star formation, galaxy formation aspects of baryonic feedback. I think the hydrodynamical simulations are not yet so far that they can really probe up to a deep redshift range on the details. Right? I could imagine that also the suppression on redshift 3 would be very small, because you have less galaxy clusters. But I think the uncertainty then of this baryonic feedback would still be very high, and in order to discriminate them, you would need a very good modeling also of these baryonic effects. I think.
No, there is. Yeah. We still need to carry out a careful analysis, and in the future we'd like to compare with Lyman alpha data or other probes of that also tell us at high redshift about the distribution of the structure.
Yes, very good. Thanks.
Thanks for your question. Okay, is there any other question?
No, I think you can go on until the end.
Okay. Yeah, well, I'm about to finish. So yeah, just before concluding, I would like just to mention that I participated in a project that we call the Hubble Olympics, where we essentially wanted to understand which are the best mechanisms for resolving the Hubble tension. For doing that, we were taking a sample of 16 different models that include the early dark energy and the dark matter decay model that I just mentioned before. And we tested all of these models against a wide compilation of data, and we used certain criteria in order to compare the success of these different models. So I don't have time to talk about this, but this was a project that was led by Niels, which is now a postdoc in Barcelona. So you have some questions about this project, I'm sure he will be able to tell you more about it. So now let me go into the conclusions. So yeah, we've seen that the lambda CDMs provides an excellent fit to many observations, but there still exists some tensions such as the Hubble tension or the S8 anomaly. And the interesting thing about these anomalies is that they could actually give us hints about the properties of the very mysterious dark sector. We have seen that the Hubble tension can be resolved by an early dark energy component, even when we add the large-scale structured data to the combination of Planck, BO, and supernova. We have also seen that the S8 anomaly can be explained by a model of two-body decaying dark matter. And apart from explaining this anomaly, this model is very well motivated because it has implications for model building, for testing on quantum excess, small-scale crisis. And what we've also seen is that unfortunately, none of these models is able to relieve both tensions simultaneously, but it could be actually that the resolution in these tensions lie in very different sectors. It appears that resolving the Hubble tension requires some kind of new background contribution, such as the early dark energy, while the S8 tension requires some new perturbation properties, such as the ones provided by the decaying dark matter model. So actually, one funny thing is that, I mean, I just said that the early dark energy model solves the Hubble tension, but not the S8 tension. Then I went to discuss that the decaying dark matter model solves the S8 tension, but not the Hubble tension. So one could just say, why not combining both? And then you get a solution to both tensions. So actually, this paper appeared last week on the archive, and they were precisely doing that. They were taking these two models, putting them together, and claiming that this works as a solution for both tensions. So, I mean, I don't find it very elegant, at least from the point of view of Occam's razor, but a priori, it's true that nothing forbids the dark sector to be very rich and complex. And this anomalies is what might be suggesting. So yeah, here I will finish. Thanks a lot for your attention.
Thank you very much, Guillermo.
Thanks.
I'm sure we will have a few more questions or comments from other people in the audience. So they can either raise their hand or speak.
I have a small question. So, thank you again, Guillermo, for the very nice talk. So you were mentioning about the supergravity motivations for decaying dark matter. Is there something similar for early dark energy, like to explain the existence of this scalar field?
Yeah, that's a good point. I mean, I just heard that what is called the string axiverse, which is the fact that string theory predicts a lot of scalar fields having action-like potential. And I'm also heard about, I mean, I'm not at all an expert on the subject, but I heard about instanton corrections, which give a value of which give a potential that have this power law, which is not just the simple cosine, but cosine to the square, to the cube. So yeah, from this point of view of string theory, I've heard, yeah, there's some models trying to predict this, but yeah, I don't know if there has been other model building efforts from in other like supergravity or other kind of particle physics. I'm sure that there must be something, but this is the only one I've heard about.
Thank you. I have another small question. When you were comparing the decaying dark matter with the case of varying neutrinos, you showed the case where you choose the mass of the neutrino to be 0.2 something.
Yeah.
Why did you choose this value? Because it seems a bit bigger than the constraint on the sum of.
Yes. Sorry. First of all, this is the sum of neutrino masses. So yes, and yeah, we know this value is ruled out. Right now, the CMB puts an upper limit of 0.12 eV, more or less. So, but yeah, we were taking this value because it gives precisely the same suppression. So it gives us a value, the same low value of S8 as the decaying model. It is like the amount, the mass of neutrinos you would need to explain the S8 anomaly. And then what we've seen is that if you have this high value of the neutrino mass, you don't fit CMB data well. So if you want, this is just another explanation of something that was already well known, that is that you cannot have very high values of neutrino mass.
Thank you.
Thanks for your question.
Okay. No more questions then? Just your last chance to either raise the hand or speak up. Okay, then I think we can finish the talk here. Thank you very much, Guillermo, for the talk and for the nice presentation. I think it has been this is a very interesting topic in cosmology and a lot of people interested in. So I wish also best luck in your postdoc hunting.
Yeah, thanks a lot.
Is coming up. It's always hard, but it's something that we all have to go through at some point.
Yeah.
And hopefully we will be able to meet in person so at some point next year or in the next years if things are
yeah, that would be nice.
So yeah, I mean, do you have any question for us? Do you want to something?
No. I mean, you said you are gonna upload the video somewhere, or?
Yes, I will pass it to the secretary, so it will be at the ICC-UB YouTube channel, and also I will upload like a version, like a reduced version with the video edited a bit, taking out the questions and everything in a personal YouTube channel I have.
Okay, yeah.
So I will send that I will send around the links whenever I see available.
Okay.
Okay. Well, thank you very much.
Thanks a lot for having me.
Everyone.
Thank you.
Yes.
Bye. Thank you.
Bye bye.
Thank you. Bye.
Bye. Ciao.